the binomial distribution. A binomial distribution is a random experiment which satisfies the following conditions. So we have two different conditions that have to be satisfied. There are only two outcomes in each trial of the experiment. Okay, so usually one would be a success and the other would be a failure. So we have two outcomes. So in general, we'll say one of those would be a success. And the other would be a failure. And it's kind of weird how we think of success and failure. Sometimes it can be a little morbid. You know, if it's success and failure, something like flipping a coin, you know, it'd be like, okay, I want to know the probability of getting exactly 3 heads out of 4 flips or something like that. That's one way. That's you know, that's kind of going along the same lines as what we've been thinking about. But what would success and failure be if I was looking at insurance claims, maybe life insurance? How do I win at life insurance? Well, if I don't die, then I never use my life insurance. So for me to win at life insurance, I have to die. So sometimes it can kind of take on that morbid tone, but not always. I just always think that's kind of funny that for me to win at life insurance, for me to benefit, my family to benefit from life insurance, I have to die. But or how do you benefit from car insurance when you have a wreck, right? Or you have to use your car insurance for something. So you can't always think of success as being something that makes you happy and that you like. I definitely want to fail at life insurance for as long as I can. All right, and then second, the experiment consists of n identical trials as described in condition 1. All right. N identical trials. So we want to have the same event go on every time. And I think I just said no, there's 2 outcomes. So that's 2 of the conditions. Third, the probability of success on any one trial is denoted by P and does not change from trial to trial. So success is going to be P. Failure is going to be 1 minus P. So if I think of success as maybe getting ahead, it would be 0.5, and then getting a tail would be 1 minus 0.5, which just so happens to be 0.5. So it doesn't have to be the same probability for each event. Sometimes if you take another statistics class, like maybe a graduate statistics class, if you're working on your master's, instead of using 1 minus P, they may use Q, because Q can stand for failure. So P plus Q, that's success plus failure, always has to be equal to 1. And again, your book, though, when it talks about failure, it usually just uses 1 minus P. But if you ever read some other article or you use some other textbook, it's probably going to use Q, especially if it's more of a mathematical-based statistics. But it's okay. It's either way. The trials are independent, so one doesn't depend on the other. And the binomial random variable is the count of the number of successes in N trials. So the number of successes would be like our X. All right, now I'm going to give you the formula for a binomial probability distribution. All right, so the probability that big X equals X is equal to NCX. So what does that mean? What's the C mean? Combination, right? So you have a combination NCX times P. What does P stand for? The success, the probability of success, to the X power times 1 minus P to the X power. I'm sorry, to the N minus X power. So what I usually do is I first find the combination, and then I'll say that answer times P to the X, and then say that answer times whatever 1 minus P is to the N minus X. Again, N is the number of trials. P is the probability of a success. And X is the number of successes in N trials. All right, so let's look for a problem. I'm still looking. All right, let's just use the one out of the PowerPoint. That way I can explain it. All right, so let's look at the example 7.4.1. It says toss a coin 4 times and record the number of heads. Is the number of heads in 4 tosses a binomial random variable? So, does it meet all of the conditions, is what that's asking. There are only 2 outcomes. Heads or not heads. All right, so we don't even think about tails. The experiment will consist of 4 tosses of a coin, so n equals 4. The probability of getting a head or a success is 1/2, and that won't change from trial to trial. And let's see, the outcome of one toss will not affect other tosses. The variable of interest is the count of the number of heads in 4 tosses. So it does meet all of the conditions. And then you can see they constructed, if you look at the bottom right of your PowerPoint, they constructed a table with the 4 events and all of the outcomes. Okay? So you can see the number of heads that they got in the different events, different outcomes, and the probability of that happening each time. So you can see there's one row for the number of heads is 0, number of heads is 1, number of heads is 2, number of heads is 3, and number of heads is 4, and their corresponding probabilities. All right. We're going to use that same scenario, or no, we're not. We're going to use something similar now to look at a problem where we could apply the binomial probability distribution formula. It says roll a 6-sided die 4 times and record the number of 6s observed. Does the number of 6s rolled in 4 tosses meet the requirements? All right, so it goes through those, and it does show that they're all met. Okay, now if we wanted to know the probability of getting exactly, say, 4 6s. You think about it. If you roll a 6-sided die 4 times, what's the probability of getting 4 6s? That's going to be the problem we work out. So find the probability of rolling 4 6s in 4 rolls of a 6-sided die. All right, so how many rolls are we going to have? 4. All right, so if we roll it 4 times and we get 4 6s, how many successes are we going to have? All right, what's the probability of rolling a 6? 1/6. What's the probability of not rolling a 6? 5/6. All right, so I can figure out the probability of rolling 4 6s by applying my binomial probability formula. All right, so I'm going to need to work out. Remember, it's NCX times P to the X times 1 minus P to the N minus X. So this will be 4C4 times 1/6 to the 4th power times 5/6 to the 4 minus 4 power, or 0 power. All right, so what is 4C4? One. All right, you punch in your calculator, or you can work it out. It's 4 factorial divided by 4 minus 4 factorial times 4 factorial. And remember, we define 0 factorial as 1. The 4 factorials cancel out, and you get just 1. Times, what is 1/6 to the 4th power? I'm not 100% sure. I can bring up a calculator, though. I know it's going to be 1/6 to the 4th power. So that's 1/1296. And then what's 5/6 to the 0 power? Anything to the 0 power, any real number is going to be 1. So here's the probability. So 1 times, well, we're not even going to do the 1, so I'm just going to do 1 divided by 1296. Excuse me. So you can see that's very small. That was 0.000, because it was to the 4th times 10 to the negative 4. 7716. So 7716. So that would round maybe to 0.0008. So it'd be about 0.08%. So not even a tenth of 1% is a chance. Not going to happen very often. If you ever played Yahtzee or anything like that, you probably have tried to get multiple numbers of the same type. So you can see very, very small chance of getting 4 6s in 4 rolls.